Okay, the second one on cumulative distribution functions, and in the previous video we introduced what they were as defined below there in the forms and the notations we can use, and it involves finding the integral of the PDF in regards to the integrating variable, which normally for what we're doing we're just calling that t. Sorry, I didn't mean to cross that out, and so we don't use the same variable as x, because that's for the continuous random variable. Okay, and graphically we have these signature shapes here with the PDF up the top and the CDF, the cumulative distribution function, down the bottom, so it accumulates up to a value of 1 for the entire relevant part of the distribution. And we looked at that in the previous video. We're going to look at a worked example and then show the shape of the resulting graph for working backwards compared to the way we were working in the previous video. Okay, the time to failure, so the time until something fails in hundreds of hours for a certain electronic component. It's based on a random variable x. Now, read carefully is the moral of the story. Cumulative distribution function, capital F. It gives you a cumulative distribution function, different to what we were doing last time around. So always keep a close eye on the provided information and read the task carefully. So it's a piecewise function, obviously based on what we learnt last time. That's the active aspect of it that we're going to concentrate on. So to go from a primitive, capital F of x, to the function f, remember going from little f to big F, we integrate, but this time we're going from the primitive to the actual function f and lowercase. So we are using the derivative. So for the active part, the top tier there, we need to take the derivative of that with regards to x. So here we go. I've taken the derivative. Better notate that properly. So what we're finding, lowercase f of x is the derivative with regards to x of 1 minus e to the negative x squared. Okay, now we've done things like that before. I just need to take care. So taking the derivative of each term, now if 1 becomes 0. Now, chain rule on the second term there. If you don't know what the chain rule is, you're definitely not watching the right video. So we have the derivative of negative x squared with regards to x. So that's negative 2x times e to the u. I'm not going to show that part. And the derivative of e to the u is just e to the u. U is negative x squared. Alright, so that remains as is essentially for our purposes here. Be careful of minusing negatives, that's a plusing a positive effectively, and we get 2x times e to the negative x squared when x is at least 0. Now we must write this properly as a piecewise function for little f of x. The PDF, probability density function, is f of x equals 2x by e to the negative x squared for x greater than or equal to 0. Otherwise it's 0, which means the complement of that domain, and that's what we got. Looking at the shape of it on a Texas Instruments Inspire, so we can use a template for a two-part piecewise function. I got a bit excited then. Alright, so we got 2x by e. So remember to use this here, don't use alpha numeric e, negative, and then x squared. Okay, and we have that as x is at least 0, and we can use our inequalities there if we want to, like so, and 0 else, so else works on this, or you could put x is less than 0, your choice. You could write the word else and it likes that, but I'm going to write this. Oops, and I forgot to type the X in. Never mind. Okay, maybe zoom in on that. It's this funny little bump there. Okay, so window zoom. Let's zoom in. Okay, so that's what we got.